Welcome to the live demonstration of our NPM, Pathfinder, Pinpoint, and Neuropixel Trajectory Explorer webinar. I am Stefan Friedrich. I'm the Director of Marketing at NewScale Technologies, and I'm joined by Ed Friedrich. He is our Life Sciences Manager. He currently manages our sales, partner, and user relations for NewScale's multi-probe micromanipulator system used by neuroscientists around the world. He joined NewScale shortly after we were founded in 2002, and he was previously at Burley Instruments, now Expo, providing marketing, sales, and support for Burley's patch clamp system for electrophysiology, along with other scientific instruments. He has more than 30 years of prior experience at Eastman Kodak, where he managed software development at the division level and later managed marketing and sales for several different business units. Thank you for joining us today, Ed. So let's jump right in. This is a quick overview of our agenda for the presentation today. So we'll shortly review a history of the NPM system, show you a sneak preview of our new modular insertion system. We will then provide an overview of Pathfinder software to start our demo, which will include a live demo of Pinpoint and NTE, and how to select target brain regions and plan trajectories with your probes, how to import those values into NPM Pathfinder software. And then we'll talk about what's next for Pinpoint along with NTE, and go into some question and answers towards the end of the discussion. So a brief history of our NPM system. So in 2015, we started receiving orders from the Allen Institute. They're located in Seattle, Washington, here in the US. And in contacting our mentor, Josh Siegel, we found that they were buying our motorized XYZ stages for acute in vivo silicon probe experiments, which were really a perfect fit for our small, precise stages. So the Allen Institute team used our manipulators to get 6 probes into the visual cortex of a mouse's brain. And our team had some experience in the patch clamp business, so we were excited about the opportunity and decided to invest in developing the multi-probe micromanipulator system, which we call NPM, selling our first system in 2016. So we're now at a point where NewScale's NPM system can allow you to control up to 8 probes simultaneously, which is certainly more than any other probe positioning system on the market. And we're compatible with Neuropixels, NeuroNexus, Cambridge Neurotech probes, Neuralite probes, and more, along with tools like syringes, and we make custom probe mounts quite frequently. So for those of you that are NPM customers, thank you for your business, first of all. And second, we wanted to show you a new system that we are making under license from the Allen Institute that will be available later this year starting on the Neuroscience Conference in October 2024. So last year, we announced that the Allen Institute for Neural Dynamics selected NewScale Technologies as its licensee for its next-gen silicon probe insertion system. And we're calling this the Modular Insertion System, or MIS, which will enable research across the entire brain with greater flexibility and more probes than the NPM system. So we'll definitely continue to offer the NPM system as our introductory product for this type of research. But again, that system can support about 8 probes, while this new MIS system will allow you to expand to more probes with a theoretical maximum of 25 probes simultaneously. The MIS system will include 3 different standard modules: a probe module for moving the neural probes, a laser module for stimulation for optogenetics, and a microscope module for visualization during experiments. And we'll be delivering our first beta systems next month to the Allen Institute. And again, our goal is to have this commercially available by the Society for Neuroscience annual meeting in October of this year. So if you're planning to go to that show, please visit the NewScale booth and you can see it in person. So how did we come to develop Pathfinder software? So as our key customers and mentors, we're using the NPM hardware and our virtual coordinate system software. We began to receive questions about how they can better plan the trajectories of their silicon probes to target regions of the brain that they wanted to explore. So some key questions would come up like, I know the region of the brain I want to explore, but how do I get there? And then also, how will I know when I'm actually there? So this brings us to today's demonstration. And so I will turn it over to Ed to show you a demo of Pinpoint, Neuropixel Trajectory Explorer, and Pathfinder, all working in parallel.
So what we're looking at here is the basic screen setup for the NPM system. Here's our viewer with a calibration block. Here is how we can control a series of 3-axis manipulators. And this screen gives us the particulars of things like polar angle, pitch angle, and so on for a particular manipulator. And I'll be talking about that a little bit later. But I wanted to start out talking about the two trajectory planning systems that we can link to and work with. And the first of these is the Neuropixels Trajectory Explorer, or NTE. And this was created by a neuroscientist named Andy Peters when he was a postdoc at University College London. And that was back about 2019. And now Andy is a professor at Oxford with his own laboratory, but continues to maintain this software and to enhance it. The other system is called Pinpoint, and this was created by the Steinmetz lab at the University of Washington, again in the Seattle area, very close to the Allen Institute. And I'm going to start with that system because it has a nice portrayal of the Neuropixels 4-shank probe. And I want to explain how we work with that probe. We're looking here at the sensory face of the probe. And this is where the metal dovetail cap would go to protect that. And that metal dovetail cap is what we grip with our NP20 probe mount. As we're looking down at that, with the shanks pointed away from us, the far rightmost shank is defined as the 0 shank. So 0, 1, 2, 3. The separation between shanks is 0.25 millimeters. And this is the Allen Common Coordinate Framework Atlas, the Allen CCF Atlas. And that's what we're going to use to do our trajectory planning. As we work with this, the mission today is I've highlighted the primary visual cortex and the LGD, the lateral geniculate dorsal area. And the goal is to take the 4 shanks of the probe and to move them through the visual cortex to the LGD and get all 4 shanks into the LGD. So we're going to maneuver the probe to do that. So as we maneuver the probe, we will keep track of the location of the 0 shank. And this is where it is right now. It's at AP0, ML0, DV0. In other words, it's sitting at bregma at the moment. And there are some important angles. This is the azimuth, which is now 0. Azimuth would swing around this way. We're at 0. This is the elevation of the probe. We're at 90 degrees at the moment. And then with a 4-shank probe, you can rotate it. Right now, the rotation is 0 degrees. To move the probe, the first step is, this is the LGD. If I click here, I pin the 0 shank into the LGD, and you can see now that the entry point has changed from 0, 0, 0 to minus 2.2 millimeters, 2.2 millimeters, and so on. So I'm nicely positioned now in the place where I want the probe to go. But now I need to change the angles so that I'm running through the visual cortex. So the first thing I want to do is change the elevation, which is currently at 90. And in the pinpoint menu, which I was trying to get to, you change the pitch angle with the F key. And so if you look at the number here, you'll see that we're dropping the elevation down to 45 degrees, which looks pretty good. And I want to change the azimuth to swing it over to the left a bit. And you change the polar angle with the 3 key. So if you look here, now we have a polar angle of 10, and we're pretty nicely positioned in the middle there. But I want all 4 shanks to be in the LGD. So I'm going to want to change this rotation of the probe. And we do that with the period key. And it looks like about 90 degrees would be good. Now I'm at 90 degrees. So that looks good. If I had had just a single shank, the position here would be pretty good in the middle. But with 4 shanks, I want to drop down in the posterior direction. And you do that with the S key. So we're going to change now the AP number, moving down. And now I want to go to the left a little bit in the ML direction. That's the A key. So that looks like we're pretty well centered. But I want to end up with the probe through the LGD. So we want to advance it. And you do that with the 0 key. And you're going to see the DV number change now. And also up here in this corner, you can see where the probe is. I think I want to maybe drop down a touch more. So that looks pretty good. So I've now used these controls. And I know that to put a probe where I want it, I'm going to want a 10-degree azimuth or polar angle, a 45-degree elevation, a 90-degree rotation of the probe, and I want the entry point to be at 4.4, 2.7, and 0.8, minus, being in the left hemisphere. I'd also like to know the coordinate of the tip, exactly where I ended up, what's my target location, which Pinpoint doesn't tell me here in this window. But if I click the arrow here, I'll put onto a clipboard a full menu of everything. And here's what the clipboard would look like. So here's this is from a run I made back on April 10th. So here's the entry coordinates, here's the tip coordinates, here's the 3 angles. And from the entry point to my target, I want to insert a depth of 3.4 millimeters. So these are all the things that I wanted to know to be able to run this trajectory. And you can see it happen very, very quickly. So the next step is, how do I set up the MPM system to actually hit that trajectory? Now, many of you are perhaps familiar with the system, but let me just do a quick review. First of all, get rid of this. Most of our systems are what we call the inverted variety, where there is a platform with a platform top that can be raised or lowered, and the manipulator rests on this arm. It can move back and forth, and that arm can be moved up and down as well. And this whole mechanism clips onto the ring structure underneath the platform top. So the manipulators all hang down, which is an advantage because you have more open room at the bottom for screens and mouse exercise equipment and so on, which is why so many people like this feature. The height of this is determined really by the elevation of the probe. If I had a really steep probe close to 90 degrees, I'd want to raise this up. A very shallow probe, I'd want to bring it down. I already have this set up for the trajectory that we're working on. The 45-degree angle works well with a height of 41 centimeters from the tabletop. So now that we have that situated correctly, now how do we deal with the polar angle and so on? Well, this is that platform top we talked about, and there are degree marks etched on it. 0 degrees is here. You remember that we wanted a 10-degree azimuth or polar angle. So in your physical system, you would move the manipulator to the point where it said 10 degrees. In the simulator, this is a simulation that we're running. I'm not connected to real probes. In the simulation, I can just say I want 10 degrees. And the same thing with the angle. Now that bar we talked about, when it is horizontal or at 0 degrees, the probe would be at 90 degrees. The elevation would be 90 degrees. If I rotate the bar up 30 degrees, the probe would be at a 60-degree elevation. We call the 30 degrees our pitch angle, and this would be the elevation. In this case, we want 45 degrees. And then we want to set up the mounting fixture so we get the probe just over our calibration block. Here's Bregma on the calibration block. Here's Lambda. We also have a place for putting in the entry point. Remember, we had those coordinates of the entry point. Here they are here. We had coordinates for the ultimate target that we're trying to hit with the tip, and we can put that in here. And the MPM system agrees that this would be the 10-degree polar angle and the 45-degree pitch angle to hit this trajectory. It also agrees that we want 3.4 millimeters as the insertion distance, the distance between those two probes. So when we get over to here, the screen where we can start moving things around, we have the buttons that can move the probe. Down here, we have a place when we're in position where we want to start an insertion. We have the insertion distance, and we can put in a speed to insert. In your physical experiment, you would want a very slow insertion speed, maybe 250 to 300 microns a minute, so as not to damage brain tissue. That would take 15 minutes or so to run if we did that here, so I put in a faster speed. Now let's look at the MPM controls for a probe. We have two modes of operation. In local mode, it says here X, Y, and Z. So this is the X stage, the Y stage, and the Z stage. And the movement will be a function of how the manipulator is facing. Since we're at that 10-degree polar angle, if I advance Y, it's just going to move forward in that direction. And every step I take here is moving 100 microns. The x-axis obviously will move perpendicular to that. And our z-axis is actually on the approach angle. So z would move at a 45-degree angle. But we want to be able to use stereotaxic coordinates, which is why we created this calibration block. And we can do that very easily. If we simply move the probe with these controls so it touches bregma, and then click get tip position, that tells us the origin of our stereotaxic coordinate system. We also like to touch lambda. That tells us the bregma lambda axis. It tells us if lambda is higher or lower than bregma, in which case we can accordingly tip the whole stereotaxic system accordingly. And once we've done that, we can go into stereotaxic mode. And where this used to say X, Y, and Z, now it says medial lateral, AP, and DV. So here's our x-axis is ML, our y-axis is AP. DV would be straight up and down. Z would be that 45-degree elevation angle that we determined. And in addition, these numbers no longer mean where you are in the stage travel. They now are the stereotaxic coordinate of the probe. We are almost 3 millimeters to the left of bregma. We're 4 millimeters south of bregma, and we're 0.9 millimeters beneath bregma. We can also, now that we're in stereotaxic coordinates, we can command the probe to go any place we want it to go. So I just double clicked on that, and I can say 0, 0, 0, go. And now we're at bregma. And back at this screen, if I want the probe to go to the entry point position, I can say set tip position. And there. Now, so we have now learned from the Pinpoint trajectory planning system what the important angles and entry point are, and we've converted those into the MPM system. And we actually only need to do that planning with Pinpoint once. From this point on, every time I want to run this trajectory from VisP to LGD, I have the setup here, and I can even log this so it's preserved for all time. So here's the setup to run that trajectory. Now, the next thing I want to do is I want to actually run the insertion, but I want to run it while looking at the Pinpoint system. And to do that, we created an architecture which we call an HTTP server, and it's going to connect these two systems. I'm launching it here. So now that server is enabled. And now, Stefan, I got to hit the escape key and get to this menu. And oh, there we go. I did do it. Okay, that worked. Okay, so now I'm at the menu, and you can see that I'm in the Allen Atlas setting, and there's another setting called EFIS link, and if I click on that to connect, now MPM is in control of the probe, but I'm seeing the location of the probe in the Allen CCF Atlas from the Pinpoint system. So I know I'm at the entry point position. I know the distance that I want to travel. I know the speed I want to travel. I can go into insertion mode and hit go. And you see now the red stop button. If I encountered some problem, I could hit stop and stop it. But now you're seeing the probe move through the visual cortex, headed toward the LGD. You can see in detail here where it is in the atlas. So this should take about a minute. When we see pink here, we'll know that we've entered the LGD.
And while the insertion is going, just as a reminder, if anyone has any questions, please add them to the meeting chat.
Okay, so we're there. And you remember that this is telling us the tip position. So we're at minus 2.2 ml. We're at minus 2.0 AP. We're at minus 3.2 dV. And those were the things that we were trying to hit in the beginning. So we planned where we wanted to go, and we got there. So that's the Pinpoint system. I should mention, after you've done an insertion, If you want to retract very slowly, you can simply make this a negative number and then retract at whatever speed you want to retract at. In the simulation mode, I can just change this back to course control and say set tip position. And I'm back to the entry point. So that's how it works with Pinpoint. I can show you quickly how it works with the Neuropixels Trajectory Explorer as well. This is the other planning system. They both work very nicely. This operates a bit differently. You don't pin the probe in this one. We start with a sagittal view. Again, here's the visual cortex and the LGD. And you just use the arrow keys in this system. So I can move it back into here. I know from this view that I want to be able to see all four of the shanks. Remember, we rotated the probe 90 degrees. You do that by hitting the control key, and you can look now here at the rotation symbol. I'm going to rotate this to get to 90 degrees. Oops, a little too fast. Okay. And now I want to change the elevation, change the angle. I do that way. I'm going to move this back. And you can see the elevation is changing here. There I'm at that 45-degree point, just as I was with the Pinpoint planning. Then I go to the horizontal view and simply move the probe into the left hemisphere and then hit the shift key and change the angle. There's that 10. Just slide over. And finally, you can go to the coronal view, and we want to raise the probe up, and you hit the Alt key and the up arrow. And here's the plan using the NTE system. Again, I can connect to MPM, connect, manipulator, new scale MPM. Okay. And now we're at the entry point, which is where the MPM system is positioned. You can see it there. And again, I can change from course mode to insertion. I've got the speed I want. I've got the distance I want. I can hit go. And now we see the probe moving in the, again, this is the Allen CCF Atlas, just a different portrayal in Andy Peters' NTE system. So in your actual physical experiment, you can have NTE or Pinpoint on your screen and be watching the progress of the probe as it's moving in the actual physical experiment. Also,
if
I should mention just one more point I wanted to make, Stefan. Um, there are two other systems that participate in the communication among these systems. One is if when you're doing your actual recording and looking at a heat map, you might be using a system called OpenEFIS that was created by Josh Siegel, who we mentioned at the Allen Institute, or you might be using Spike GLX, which was created by Bill Karsh of Genelia. Josh and Bill participated as well in this collaboration. And so as you are doing the insertion, the NTE system can take the brain location and send it to OpenEFIS or Spike GLX so you can see in the heat map what brain region you're in. Same thing with Pinpoint. Pinpoint can do that as well. So it's a collaboration among Neuropixels Trajectory Explorer, Pinpoint, NewScale with our MPM Pathfinder, the Allen Institute with OpenEFIS, and Genelia with Bill Karsh. This was a team of people who collaborated to create this architecture so it all works together. And that's it. Okay, Stefan.
I have a question here about the different atlases. The question is specifically about a rat atlas. Pinpoint has a rat atlas available. They're also working to incorporate other types of atlases. So if you have a specific atlas request for these teams, they're very happy to work with you and try to incorporate those atlases into their tools. There's a question here about using a NeuroPixel on a rotating mouse and getting the electrical signal through an electrical slip ring, I believe that is. I'm not sure on the answer to that question. I will send that question over to one of our partner neuroscientists that might know a bit more about the NeuroPixels probes. We don't sell the NeuroPixels probes, so I'm sorry, I'm not sure how many channels that electrical slip ring should be. One other question we get quite frequently is whether you can do simultaneous insertions of multiple probes at once, which you certainly can. Our demonstration was just for a single probe, but if you're using the MPM, you could do up to 8, or with the new MIS system, you'll be able to do up to 25, and you can insert as many probes as you want simultaneously at the same
Right.
time.
So you would, in the case of the Allen Institute, for example, they would have 6 probes positioned in the visual cortex, and they would hit the go button to insert for the first, then they'd hit it for the second, the third, the fourth, and they can have all 6 advancing at the same time.
Many researchers insert very slowly, as Ed said, usually in the 200 to 300 micron per minute range. So being able to do multiple probes at the same time saves a lot of time during the experiment, especially when you're working with many probes at once. I don't see any other questions here. So again, as Ed said, we're happy to help anyone that's interested in having a private demonstration, or if you'd like us to plan a trajectory for you, we're happy to do that. So please reach out to us. I think most of you have been working with our distribution partner, Leeds Biotech in China. So they're certainly also happy to help and answer questions as well. Oh, we do have a couple other questions here. Minimum speed of the manipulator. So the resolution of the linear stage that we make is 1/2 of a micron. So those are the smallest steps that you can do with the manipulator. So I suppose, you know, a minimum speed could be as slow as 1 micron per minute, but that would take a very long time. I am current NPM user, and I see the NeuroPixel tip rotating a bit. Why could this be? Depending on which probe mount you're using, that may explain some of the rotation. If you could send us a photo of the issue, we'd be happy to help answer that. One request we've been receiving for the new 4-shank probes is to be able to monitor the rotation of the 4 shanks. So we are working to develop a new fixture for that so that you can measure the exact rotation of those 4 shanks, and then you can better plan your trajectories and experiments with a very precise reading on that angle. But if the tip of the probe is rotating or moving within the probe mount, it may be an issue with the installation. So again, if you could send us or Leeds a photograph of that, we would be happy to help answer that question for you. I don't see any other questions here. So again, if you have any questions, please do send them to either us or the Leeds team directly, and we would be happy to help you all. Thank you all for your time, and we hope to hear from you again soon.